Yeah, sometimes in connection to the quizzes, there can be problems in the recordings and restarting the presentation. So just in case, 2 videos. Okay, so just before I got ill, we talked about explainable AI and quite a variety of methods. So as a brief summary, just this particular plot, we looked into the black box and how you could make these methods explainable or use interpretable methods in the first place. And today we will focus on a completely different topic, but at the same time it's not completely unrelated, because often unsupervised learning is used to make data structures more interpretable, right? So you try to find structure in data, and as a result it might be easier to interpret those results. And there will be, I mean, talking about unsupervised learning in one single lecture is really difficult to show the full breadth of this domain. So we'll focus on a few standard approaches that everyone should know if you haven't heard about it before. So I will run through these methods very quickly. And then I will show you a few examples that are very specific to meteorology and climate science, because there we have a very specific view on this, and also for a very long period of time, and about how states evolve from one pattern to the next. So I will try to focus a little bit on this and give you an intuition for how some of these methods might actually be easier to understand from an application point of view than they are to understand if you just worked with the theory underneath this. So yeah, more to come. If you want to read up on this, which I can just strongly recommend, here these methods are actually quite well established for decades. So it's well worth reading books about it. And not just in, let's say, the classic deep learning book here, which I actually put only at the 3rd reference here. I think more specifically for this lecture, the Wilkes 2006 book here, which is originally a statistics book for atmospheric scientists. It's quite interesting to look at as a sort of comparison, especially for principal component analysis and its rotations, as compared to some of the standard computer science textbooks. And similarly, Hasty is always a good reference, so the updated version of edition 2, which was corrected and reprinted in 2017. By the way, if you have struggled, if one of the reasons why you might not read this is that you can't find a book or don't have a PDF version, I have PDF versions of all of these. Okay, so send me an email if you really struggle to get access to those. But usually they're quite easy to find online as well. And otherwise, especially for the applications, again, blog posts and papers are quite relevant. So I don't think I have to spend too much time on this. So we had a lot of supervised learning so far. Today we will talk about unsupervised learning. So the focus shifts for one day in particular. And later on you will see again how you can couple this to supervised learning methods in the first place. And to put this really simply, so supervised learning, we had labeled data, right? So we didn't just have predictors, but we also had predictants, and we tried to, let's say, formulate a regression or a classification problem. In unsupervised learning, its most basic form, it's really just we have data, which is typically high dimensional. So you have still, just like we had many predictors, high dimensional regression problems, classification problems. You could still have thousands of features characterizing something that you might be interested in. And you try to dimension reduce this in some way or find commonalities, common structure in this data. So discover patterns in the broadest sense of the word. But it's going to be high dimensional still because it's machine learning, even though some of the visualizations I will show will be for 2D examples, which are obviously just for visualization purposes. So always when you see these visualization examples, think of it in higher dimensions, which just makes it slightly more difficult. So again, in a nutshell, why unsupervised learning? Usually it's to uncover patterns in this high-dimensional data. Often it's also to find proxy features that summarize information in an interpretable way. So we will especially talk about this in the context of PCA Varimax, and then it's a bit of a question of how you formulate these proxy features to make them interpretable in the first place. Then dimensional reduction plays a big role, so often you have a lot of correlated features, say, that contain the same information, and you want to run a really complex regression algorithm using these data sets as predictors, these features as predictors, and then it makes sense to summarize them by these proxy features to have fewer predictors in a lower dimensional regression or classification problem. not just to increase interpretability and fight the curse of dimensionality, but also to speed up the training process, because as we touched on in the module evaluation, it can be a bit tedious sometimes to wait for so long. Now, a little anecdote: when we talk about unsupervised learning, this is often connected to a concept called Occam's razor, which is the classic. It's a larger concept, and many different interpretations of it exist. And I guess there's a specific one for machine learning in the sense that we always have to find a complexity accuracy trade-off optimum. So let's say in the machine learning world, that the analog of this, not perfect analogy, is that if you had two machine learning models, one is much easier to train and much more simple, maybe more interpretable, but it gives you the same quality of predictions as a more complex model, then maybe go for the simpler model, right? Because it has variety of options. You might have heard about this in physics as well. Maybe as a little bridge to remember this. So Occam is often written in this way in the scientific literature. It goes after William of Occam, a 14th century friar. And I got a little confused because I think I told you before, I lived in the UK for a while. I liked cycling, and cycling through Occam Village is actually quite a nice ride if you cycle from London out into Surrey. So I cycled through this village and thought, does that have anything to do with Occam's razor? And yes, it had to do, but it was striking to me that the writing that we commonly use is very different to the writing of the village's name. Yeah, just to give you a bridge here. And I think Occam wasn't actually the only one thinking about this at the time, or just people didn't communicate so much. So many people came up with similar ideas over the centuries before they actually found out that there were similar ideas around. Now, to give you one example that you have already encountered in Hackathon 1 to a certain degree, but in a different formulation of how unsupervised learning can help to speed up algorithms. I just point to this paper very close to the Hackathon formulation, where we try to predict or parameterize ozone in an Earth system model based on physical, meteorological variables, and usually then, trying different machine learning approaches to perform this mapping. Now, in the Hackathon, you actually used column information only, you might remember, which was partly motivated by how it's parallelized in the Earth system model, but also allows you to work with a lower dimensionality. But originally we performed this on the entire, let's say, temperature state of the atmosphere, which means you had a lot of hundred thousands to millions of predictors. And for this, it's very useful then to apply something like PCA, principal component analysis, that we talk about today, in a slightly different fashion to what you are certainly used to, unless you took meteorology stats, to perform a dimension reduction to, let's say, just keep the 1,000 most important proxy features, so to speak. And that can speed up things a lot. This was the main motivation in this case, to speed up the regression algorithm afterwards. Could maybe someone mention what a slight disadvantage with this two-step procedure is if you want to perform a dimension reduction? If you do this on the predictors first, and then do a regression afterwards? What could be a potential issue? Well, one issue, maybe it's going too many steps in advance, but I think the idea is quite clear once you hear about it. So clearly in a regression problem, you look for information in the predictors that predicts the predictants, right? Whereas if you do an unsupervised learning approach on the predictors first, without looking at what you try to predict, it could be that by dimension reducing, which usually means you lose some of the information, you filter actually out most of the information that you might actually need to predict predictants. You just find the most important patterns maybe in the predictors, but maybe the most important patterns in predictors is actually not what is predictive of ozone in this case, right? So this indirect connection is somewhat unfortunate in this sense, but it makes it computationally cheaper, which is what we wanted to achieve in this case. An alternative could have been, I will briefly touch on this later on, if you used an autoencoder which tries to sort of do the dimension reduction, maybe a reconstruction in one go, so that you do your dimensional reduction depending on what you try to predict or so. But again, that's just going to be computationally expensive in a different way. Okay, so very brief recap, an algorithm that most of you will have heard about, and at least if you attended one of my first lectures of this module, is the k-means clustering algorithm. I'm just talking about this again because it establishes a nice baseline for what unsupervised learning can do. It's particularly easy to visualize in a 2D plot. So let's say you would have a data structure of two features, right? Because we look at 2 dimensions. So this would be this data cloud given in green here. So apologies if you're colorblind. I should have maybe used PowerPoint to change that slightly. But let's say you try to group this data into clusters, in this case 2 different clusters, and you initialize those randomly. It doesn't quite seem random. It's mostly for demonstration purposes, I suppose. But one centroid shown in red here on the right side, which is clearly outside the data cloud, and one centroid outside on the left side of the data cloud. And now what k-means clustering does is to look at the sample evidence, and using a distance metric like Euclidean distance, you can also think about more complex distance metrics, but that's the most commonly used one, to establish which points fall closer to the red centroid or to the blue centroid. And then basically what you do is to update the centroid position in the usually high dimensional feature space according to the average or median position, for example, of these points associated with the centroids. So this shifts the centroid towards the center of mass of the red and the blue dots. And then you run this procedure multiple times, and eventually you come up with a quite neat separation of the 2 wings of the distribution here. What you can immediately see is, and this is why I refer to this as hard clustering, is that in this formulation here, by color coding, basically you associated each point, even if it's exactly on the decision boundary here, with one specific cluster. So you say it's 100% belonging to an individual cluster, which is clearly not perfect in a world which is usually behaving in some smooth way, right? You don't just change from one point to the next. You don't have 2 truly separated data clouds or high-dimensional data clouds. And also when you do this, I showed you this plot before as well, you can come up with a lot of different ideas of what you are actually after, right? So I indicated this before, but looking at data, what type of clustering you want to do, how many clusters you want to find. There are certain metrics you can use, especially for k-means clustering, and I will not talk about them today, because if you're interested in clustering, you probably consider k-means as a baseline, and then it's very easy to talk about, let's say, elbow plots or silhouette plots. But so you will find out anyway, so I don't have to talk to you about it. But what is clearly down to the scientist or to the application is, what are you interested in the first place? Are you just interested in 2 groups here, or are you even interested in some sort of hierarchical clustering where you first identify, let's say, 2 different groups, right? And this group you split up into 3 different groups, right? And then actually the tomatoes you could further split up into upright tomatoes and one tomato that does something slightly strange and lies on the side, right? So you could think about different ways of structuring this data, both in a sort of flat hierarchy or in a vertical hierarchy. And this brings me directly to the unsupervised workflow. So usually what you have is, as I already mentioned many times now, a high-dimensional data array, and then you try to measure pattern similarity, just like you saw on k-means using the Euclidean distance, the cluster association, usually get out some level of clusters or features or factors in the end that define a grouping. But typically, once you have done this, it's pretty much down to you to find some objective metrics, which is usually hard, or some more subjective ways, according to your problem, to reformulate this presentation, right? So you could already pre-process the data in some way to more clearly show what you want to find. Clearly, you want to do this in a way that you're not just reconfirming your bias, your subjective bias, or you might want to change how you measure pattern similarity or how many groups you want to define in the first place to be able to distinguish what you want to find, right? So if all the tomatoes are in one group, but you want to find this one single tomato that does something different, then you might have to increase the number of clusters you're looking for. Okay, and there are many different ways to do this. So once again, I think there are multiple strategies to go about this. So what I will do is to run you very quickly through a few main ideas without going into too much nitty-gritty details about the algorithms. So this will be a few more clustering approaches and something called self-organizing maps, which you see quite frequently applied in meteorology. And then I will talk about principal component analysis and its rotations in somewhat more detail, because that's also important for your assignment. And it's a very fundamental method to use in meteorology, and also good to understand in somewhat more detail. And I think because there's so much literature about its applications in these domains, it's actually sometimes easier to understand it this way than in a linear algebra lecture. So talking about different clustering methods, we talked about k-means clustering, which is sort of this flat way of distinguishing between samples and associating it with clusters. An alternative would be hierarchical clustering. So you could think of ways to first define each sample as its own cluster, and then to put together clusters right until some sort of stopping criterion. You find common space, right? And this could be written in a hierarchical structure, bottom up or top down. It doesn't really matter, but usually it's defined this way. Or alternatively, you could start with the entirety of samples, right, and just split the samples progressively. Like I said, maybe first vegetables and fruits to animals, and then inside the vegetables, pears, apples, and tomatoes, and inside the tomatoes, tomatoes that stand upright and tomatoes that lay on the side, say. And typically these splits are determined in a greedy manner, so locally optimal, because otherwise they become very expensive and visualized in such dendrograms. And the key always in clustering algorithms is how you define distance between clusters and how you or linkages alternatively to merge samples together. The next big category, I would say, is fuzzy or soft clustering, so as opposed to hard clustering. So when I said k-means is a hard clustering algorithm because it associates strictly a sample with a certain cluster, you can easily think of ways to not be so harsh and have associations, membership matrices that define if a sample, let's say, has a certain interpreted probability of belonging to one of the clusters or to all clusters, right? So a sample could, in principle, to a certain degree, have a likelihood of belonging to one of the clusters. Maybe sometimes 80% belonging to this cluster and 20% belonging to another cluster if it's on the close to the decision boundary. In other cases, this might be more clear-cut. And the famous algorithm that, again, some of you will have heard about is the fuzzy c-means clustering algorithm, which I linked here. But again, this is just about concepts, not going into too much detail. Because what is actually, from my point of view, more specifically adapted or used in climate science and meteorology is something called self-organizing maps. You might have heard about it under the term cohorted networks instead, because it was invented or suggested by Tuvo Kohonen. This is basically a neural network approach because it uses a few layer neural network approach in the sense that it uses nodes to abstract the data into feature maps. So I think it's a great example where you can see that looking at something like meteorology, where you have a spatial domain that you can visualize, is really helpful to understand the method in the first place. So often if you look online, you will find, and again, I think it's not great for if you're colorblind, I apologize for this, but you will find plots like this where you have an input layer for a self-organizing map. So this could be some sort of feature vector that is high dimensional, and you look for similarities of that feature vector to weights of neurons. So each of these shapes here is a neuron, so to speak, which is already an abstract form. Why is there a single neuron? The neuron has a number of weights, and the weights characterize various states of the system. And the color coding here, that you have blue in the top left corner and upper row and red in the lower row here, usually this is done on a 2D grid in some way, because this way you can visualize it. You will see examples of this later. But the color coding implies that the nodes down here in red or in orange are more similar to each other. So nodes on the self-organizing map with a similar color here, or that are close to each other in topological space, as you will see, will be more similar to each other, and most distinct, sort of lower right corner would be most distinct from the upper left corner. But what you want to do is a dimensional reduction that maps onto those weights, so that each of these nodes on the self-organizing map output represents a characteristic state of the system. And basically, by having a continuity where nodes that are close to each other on the self-organizing map are more similar to each other, you have a smooth topology, as we call this, right? So you might be able to better reflect a system which smoothly transitions from one state into the next, because, for example, a given input that is close to another input in terms of how similar it is, whatever that might be, should on the self-organizing map be close to, so they should map onto nodes that are close to each other. Does that make sense? So if you have closeness in the input space, you should have proximity also in the output space, which in this case, in the clustered space, would be the position on the self-organizing map. And it's a nonlinear method, which is also important compared to some of the other methods I discussed later like PCA. And the important thing is, again, that it maps a high-dimensional input in a smooth and ordered fashion onto typically a 2D map of these nodes, which are characterized by neurons or weights within those nodes. And you will see that to define while you are updating or learning those node representations, you will use something called a neighborhood function, so that you get sort of a soft clustering or fuzzy clustering impression in which each feature vector, say x, will be mapped onto, compared against those weights for each individual node, and then you will define the best matching unit that is closest in terms of defining the current input to the state presentations that you have. And then you will not just update the best matching unit according to this new sample when you train the algorithm, but you will also update to a smaller degree neighboring nodes on the grid. And by this, you get something that is topologically similar. Now, a key hyperparameter is how many nodes you would have then here in columns and rows, for example. That's a hyperparameter to be defined to characterize your self-organizing map. But the key point is you get a smooth topology so that different parts of the SOM respond to similar inputs and vice versa, the mapping. So let me just run through this, and then maybe we can have a 2 minutes break. So the SOM algorithm, in a nutshell, can be summarized as this. You have a vector x characterizing an individual sample. This will be high dimensional, let's say L features. And you map this onto the SOM nodes, of which there are m times m row times m column times nodes on a two-dimensional grid, typically. And each of these nodes has certain weight vectors associated with them, which you can also visualize, as you will see later on. And then there's, again, similar to k-means, a necessity to initialize the weights in the first place, and there's smart ways and slightly more silly ways of doing this. The silly way would be to do it randomly, because usually that slows down convergence and leads to slightly less robust results. So you might get slightly different results. The results will not be as consistent, or you could use something like the principal component eigenvectors, which you will hear much more about towards the end of the lecture. But it's not so important for the concept here. And then you go through an iterative procedure where you choose a random sample from your sample matrix, right? So you would have, let's say, n samples, and you choose one of them. You find the best matching unit, the BMU, by the distance of the sample to the weights of this node. Typically use for this something like the Euclidean distance. But again, that's down to your choice, but it usually doesn't make such a huge difference for most applications. And then the key aspect that sets it apart from k-means, and really, depending on how you formulate it, it's really the key difference from k-means in the first place, is that you have this neighborhood function where you can, for example, use a Gauss function, but there are various ways of doing this. Gauss is probably the most common one, in which you define a neighborhood subject to a learning rate, which is a pre-exponential parameter, which depends on the number of steps you have already iterated. And this is usually monotonically decreasing so that to ensure convergence and to decrease the environment on the SOM nodes in which the new sample will again update this map. And then you basically measure the distance to the best matching unit. So for the best matching unit, the update would just be equal to alpha s, right? Times, let's say, the distance between, you will see this next, so the updating factor, right, by which this is scaled would just be alpha s. And for nodes on the SOM, m times row, m times column map, that would be something slightly smaller, right? And usually it's decreasing because you also adjust sort of the neighborhood scale on the SOM map is also decreasing because you also adjust this sigma parameter in the kernel. And finally, you update the weights after each step according to the previous position times the scaling that you got here. So this will get smaller and smaller as you iterate, just by definition to ensure convergence, times the distance between the current sample and the weight vector for each node. But each node could potentially be updated in every single such iteration, in contrast to k-means where only the best matching unit would be updated. And I told you when I said I want to talk through this, I wanted to talk through the self-organizing maps, so I need 2 more slides after this. So just to give you an example of how this leads to different results from k-means, one aspect where we applied this is large-scale meteorological patterns over Europe. So classically we know, and I've mentioned this a few times already, that there are certain high pressure systems that can sit over Europe year-round, but also during summer, where over multiple days you have basically a high pressure system that gets stuck and produces heat waves over certain regions. So this is just for a few months ago. You might still remember this event where beginning of September we had very hot conditions also over Germany, the UK and France. And simultaneously with this, because this is called an omega block, you see this high pressure system that is not to be moved for quite a few days sitting over Central Europe. And on the edges of this omega shape, you get low pressure systems with excessive rainfall. So you might have heard around that time that there were heavy rainfall in Thessaloniki and regions of Greece that were also associated with this large-scale weather situation. So if you have, let's say, a long climate model simulation, you sometimes ask yourself, does a feature like this, an omega block like this, right, become more frequent in future climate simulations? Does it become less frequent, for example? If you have thousands of years of simulations because you have to calculate a lot of statistics, this becomes very tedious to manually label. And indices off the top of I say there are some index-based approaches, right, which look, let's say, at the geopotential height gradient across a certain latitude or so, but you can imagine that they are not very adaptive to specific situations. The weather system might just be shifted by a few degrees latitude, longitude, and so on. So what we did a while ago is to focus on the high pressure events during summer. This was Carl Thomas, a PhD student of mine who graduated a few years ago. And using self-organizing maps at trying to find common states that are typically associated. So using self-organizing maps to get abstractions of states, and then using combinations, the actual true story is somewhat more complicated, combinations of these states to define atmospheric situations, dynamical situations, which are commonly associated with blocking. I don't want to go into the nitty-gritty detail again, but just for illustration purposes, it's quite nice to show you how a self-organizing map is learned. So at the beginning, you start, this is not great with the timer here, but you start with a 3x3 map. In this case, just for illustration purposes, you could also choose a different configuration, let's say 4x4, 5x4, 3x5. It's down to what you think is realistic in the end, yields the most realistic results. But you start with some initialization of the SOMs, and the smoothness of these plots implies something wrong, which is really that what we look at is a dynamical variable called geopotential height. I'll put this on the next slide, where for each individual grid point, you look at geopotential height anomalies. And if you have a positive anomaly, it's basically a high pressure field. If you have a negative anomaly, it's a low pressure field. You have to initialize these in some way. In this case, we used PCA eigenvectors, And then you iterate this a few times, and then you might have arrived at a 3x3 map like this, where, again, just to iterate this, each of these maps is a single SOM node, right? And each of these nodes is associated with a weight vector, which is now represented on these maps, right? So the weight vector will just represent, let's say, a positive geopotential height anomaly at a certain grid point, grid location of that map. And what you can already see here is that after the initialization, it doesn't quite look like the initialized feature anymore, right? It has reshifted. But now you have these node-specific weights, and you can contrast this to a new sample day, where you have a huge low-pressure system sitting over the UK, in this case. And then you have to find the best matching unit, which in this case is still quite different, but just because of the negative anomaly here, I guess that's the best match. So this would be this function here. And then you would update this best matching unit. And it's very hard to see on just a single sample basis because the update is per sample quite small. But you do this over many, many samples. You would not just update this particular map, which gets clearly updated most strongly, but you would also update the surrounding maps, the surrounding nodes on the map based on this neighborhood function. And then you do this many, many times until you arrived at a final self-organizing map that has converged. What you can see is the smooth topology, right? So you have in the top row features with positive geopotential height anomalies over Northern Europe, and in the bottom row, which is most distant on the map, negative anomalies over the Northern Europe. And in between, you would see maybe, first of all, this Northern European high-pressure system disappearing and giving way in this dimension to a low-pressure system over the UK, over the British Isles. Whereas here, you would transition from a Central European negative geopotential height to a Northern European geopotential height. But just the most distant features you would basically see on the opposite ending corners. Okay. So why is this important? Because if you compared this to, let's say, k-means output, and you would do this, let's say, for 20 clusters, right, or 20 nodes for the SOM, you can see that k-means will not produce a smooth topology, right? Each node will just be trying to be as different as possible from the rest of the data set, right? Each cluster. And you don't get a smooth topology of states that, let's say, on one day you're associated with this state, so on the next day you might move into this state with greater likelihood, then jumping from this state to next into this state. So it just represents the smoothness of the actual system in a better way. Now, as I said, the only difference between k-means and SOMs is that fundamentally, in a conceptual way, is that you have this neighborhood function. So if you have very few nodes in the first place, SOMs will also try to be particularly orthogonal, right? Because you're sort of running into this problem that you want to represent all different states of the atmosphere, but you don't have enough nodes. So this is just concerning the number of nodes you have to choose in the first place. You don't have enough nodes to model a smooth transition between states. And in that case, SOMs, so if you had just 4 nodes, you basically then run into this case where k-means and SOMs yield very, very similar results. But yeah, we also showed in this paper then, as a result of k-means not being particularly realistic representations of the actual smooth topologies, you couldn't define a particularly good way. So SOMs were superior in defining blocking associated sequences of atmospheric states compared to k-means. Okay, on this I might stop. If you want, who would be in favor of a 3 minutes break? Yeah. Any questions about this so far? I mean, it's actually quite. I think the mapping, what these weights represent, is very difficult to get for specific applications. But I think for meteorology, it's quite obvious because you have these gridded atmospheric states, right? We have gridded data, so each grid point represents a feature. So you can actually visualize quite easily what the weights of each node on a self-organizing map represents, which would be, let's say, one node representing generally states. So states would be associated with this node which have a high pressure system sitting over Scandinavia and Eastern Europe and Russia here, right? Whereas for many other applications, it's not so easy to visualize what the weights represent.
So the way to interpret it is basically if we have new data that we want to know if it's classified as a low pressure or high pressure system, then we just fed that into the SOM and then compute the correlation index for each of these nodes.
Yeah, so that's the next step, right? So once you have this unsupervised representation of your atmospheric states, it's put down to you how to interpret this, right? So, and how to use it. So yeah, I mean, if I just looked at this 20-node map, I would say, yeah, generally states in the upper left corner are associated with low pressure systems, states in the lower right corner are associated with strong high pressure systems over Northern Europe, say, right? But then it's, again, this feedback loop. Does that tell you anything that you are interested in, right? So what we did is to look at a ground truth data set we labeled for blocking events and say, on these extreme heat wave days, which are usually lasting for at least 5 days in a row, which sequences of these maps were typically associated with a heat wave, right? And from this, we could then validate, sort of establish a mapping between these atmospheric states and heat waves, and then try and validate this on an objective ground truth data set that we hadn't used for defining this label, because you want to cross-validate this in a way. And we could show that this outperforms all the index-based methods that had been defined before. But how you use it basically is down to you, right? In this case, we wanted to map it to the heat wave events. A different application could have mapped it to the flooding events, right? In that case, you would have been interested in different nodes of this kind. But how would this be applied operationally? You could use this now for climate model simulations and look at thousands of years of simulation and just say, if we have, let's say, 50 node sequences that are typically associated strongly with high precision and recall, with blocking and the heat waves, can we see that these node sensor sequences in terms of statistical frequency of occurrence change a lot if you force the climate model by a lot of CO2 global warming, right? Without having to analyze those 1,000 years by hand. Okay, I'm not sure if this counts to the 3 minutes, so if you break. Any other questions on this? But Park, was that clear to you? So it depends. You have to tie it to so once you have these atmospheric states, you have to think about, are these representations useful? Can I map them onto, let's say, a heat wave I'm interested in? And then automatically apply this mapping, this association for future data sets or so.